Today we're going to talk about isotopes, and we're also going to add with that this idea of average atomic mass and what it is that we're talking about and how isotopes affect that average atomic mass. Just a little review, a quick review of the atom and the things that we've been talking about. If you change the number of protons, then it will affect the identity of the atom. Reminder, you cannot change protons without changing the element, and the result will be a completely different atom or a completely different element. If you change the number of electrons, and we just got done talking about this, it will change the charge, and when you have that, then its result will be an ion, and we just finished with that conversation. Another thing that we talked about is neutrons. If you change the neutrons, it will change the mass, and the result will be an isotope. So today we're going to learn what that to put that all together. For an example, hydrogen has 3 isotopes. There are 3 different versions of hydrogen, and we see those versions right here. We have one protium, which has 1 proton, deuterium, which has a proton and a neutron, and tritium, which has 1 proton and 2 neutrons. Note that, however, that the number of protons never changes. If you change the number of protons, you change the element. Again, looking at those same 3 versions of hydrogen, we notice that having more neutrons does increase the mass of each one. However, it does not change the element. It is still hydrogen. So what we're looking for and what we have here then, hydrogen with those 3 isotopes, 3 different versions. This one, protium, has a mass number of 1, and we have deuterium with a mass number of 2, and tritium with a mass number of 3. So then the question becomes, why does the atomic mass on the periodic table have so many decimal places? And why then when we find carbon do we find the number 12.0115? And our table isn't quite as long as some of these, but we'll notice that they are all decimals. And we're going to talk about today the why that they're the decimals. The atomic mass is the one number that best represents the mass of all 3 versions of hydrogen. And so what they're talking about here is this number is an average of all 3 of those different versions of hydrogen. No version of hydrogen anywhere out there in the universe actually has this mass of 1.00797. What they're talking about, again, that this is just an average of all 3 different isotopes of hydrogen. So when we look at that number, this number is a weighted average of the masses of every isotope of hydrogen, not just the one. And so that's what we're looking for today, is how they actually go about figuring that number. Just a couple of things before we get to the math of it and how we do it is this idea of percent abundance. Percent abundance is how often the isotope occurs in the sample of the element. And what we're looking at in this picture here is a sample of magnesium. A sample of magnesium collected anywhere in the universe is going to have 3 different isotopes of magnesium. So what we're talking about with magnesium and this idea of percent abundance, these are the percent abundances of each of the magnesium isotopes. So we've got our sample here. 78.9% of magnesium will be magnesium 24. And what that's telling us then is that is the magnesium that would have 12 neutrons. And so 79% of the time, or I rounded up, 79% of the time we're going to find magnesium with 12 neutrons. 10% of magnesium, though, however, will be magnesium 25, and in that case we would have 13 neutrons. And 11.10% of the magnesium will be magnesium 24. Actually, I think that's a typo. That should be magnesium 26. And of course then we would have 14 neutrons with that. When we're dealing with this information, this data is either going to be provided to you in problems, and most of the time the problems that will come to us in this form right here, or given to us in a table where we can look it up. I don't expect you to memorize those numbers, and I don't even have them memorized. So they're out there, but we'll be giving them to you. We got to convert them to be able to use them, though. Okay, so we're going to calculate a weighted average, and we're going to use the example of magnesium we were just given. We're going to take the mass of the isotope number 1 of magnesium, and that was 24. And what we're going to do is we're going to take the percent abundance divided by 100. Well, the percent abundance was 78.90%. And so you can do that divided by 100, or if you do that, you'll simply understand that you just move the decimal point 2 places, 1, 2, and so you're going to have 0.7890, and then you multiply those two numbers together. So 24 times 0.7890, and that gives us 18.936. And so we take the second mass of isotope number 2, and so my isotope number 2 was 25, and the percent abundance of that was 10%. And again, we'll move the decimal point 2 places, or divide by 100. So we'll take 25 then times 0.10, and that will give us 2.5. The mass of isotope number 3 was 26, and we'll take that 26, and again the percent abundance was 11.10%, so we'll move that decimal again and come up with 26 times 0.1110, and we'll get 2.886. And then the next thing that we're going to do is simply add together 18.936 plus 2.5 plus 2.886, and that will give us the average weighted mass, and that would be 24.32. Okay, so this sample question was one that they'll give it to us in a chart form. We're going to take the 3 different isotopes of hydrogen, hydrogen 1, hydrogen 2, hydrogen 3, and we're going to calculate the average atomic mass for hydrogen. The mass of hydrogen 1 is 1.0078, and the relative abundance is 99.985% of the population. And so again, we will move that decimal 2 times, so we'll have 0.99985, and we'll go ahead and do the math of that. So 1.0078 times 0.99985, and we will get an answer of 1.0076. And then we'll go ahead and do the second one, and it has a mass of 2.0141, and we'll multiply that again. And this time you notice that the population of hydrogen 2 is very, very small, but we're still going to go ahead and move that decimal 2 places, and so what we're going to be doing is adding 2 zeros in front of that decimal, so we will have 0.00015, and then we will go ahead and multiply that, and we'll get 0.0003. And then the third one we notice, and occasionally this happens, that has a mass of 3.0160, and it's a trace amount. And so when we see that, we count that as a 0. And so it's actually not going to affect our mass. It is out there, but it exists so very rare that it will not affect it. And then what we'll do is add those 3 together. 1.0076 plus 0.0003 plus 0 will give us the average atomic mass of 1.008. We label those with an average atomic mass unit, and that's what we're going to label those with, is AMUs. We'll do one more, and then we'll let you practice on your own. So we'll take lithium-6. Again, the mass of lithium-6 is 6.0151, and we multiply that times the population of 7.42%. So again, we move that decimal. A lot of mistakes are made moving that decimal and not realizing that you can't just put 0.742. You must get that 0 in front of there. So if we go ahead and multiply that out, we're going to find that it comes to 0.4463. And we take our second mass of hydrogen, 7.0160, and we multiply again by moving that decimal times 0.9258, and we find that we get 6.4 0.4495. And so we go ahead then and add 0.4436 plus 6.495, and we get an average atomic mass of 6.941 AMUs. Sometimes these are going to be in the form of a word problem, but it's no different. You just have to pick out the numbers that you need to use. Go ahead and try the last one on your own and have it ready for tomorrow.